In this video, we would like to find the Fourier transform which we represent by x of j omega for the time domain signal x of t, which is an exponential given by this expression, and it is given that a is greater than 0. So uh, if we observe our x of j omega, let me write the expression for x of j omega, which is the Fourier transform of x of t. So if I write an expression for x of j omega, we can write it as minus infinity integral from minus infinity to plus infinity x of t and multiplied by e raised to power j omega t dt. So we actually need to evaluate this integral. But before that, I would like to give you the graphical representation of x of t, which is actually given in this equation. So if you have a good if you can visualize x of t, then hopefully you would be able to easily understand this integration as well. So let's see, let's try to observe x of t graphically. Right? So graphically, I am interested in visualizing this signal x of t, which is given as e raised to power minus a mod of t with a greater than 0. Now if you observe, before solving it, let's try to draw this signal first. So if you observe, here we have we have a, which is some constant, and it is given that a is greater than 0. It means a is positive. A is positive, right? So then we have t, time axis. Time can be negative as well as positive. So if I draw time axis and I say this is my 0, all points over here, right, towards the right side of this 0, all points, let me draw it specifically, 1 2 3 4. For example, this is 1, this is 2, this is 3, this is 4. All are positive, and all points towards the left are negative, right? Minus 3 and minus 4 and so on, right? So if you particularly observe this time axis, you have 1 2 3 towards the right, and minus 1 minus 2 minus 3. But here we don't have t, we have the mod t, which is actually known as the absolute value of t, right? And as you remember, if you observe mod of some number, let me recall that if you have some number, in general, if you have a number a plus j times b, and you want to find its mod, basically it is to find the mod of this side, and you can write it as the square of a plus square of b. So actually this is always you will get some positive value here, because the square of a and square of b would be positive, and if you take the square root of some positive number, that would be positive, right? So this is how we get the mod, the absolute value of t, right? So you can find the absolute value of t, and if you are if you observe this, this, that t basically is just 1 2 3. So t, suppose t is equal to minus 1, and if I am interested in finding out its absolute value, the mod, right? So you can say minus 1 plus j0, and I always can write it as minus 1 square plus 0 square, and that is actually equal to plus 1. right? So the mod value here is for -1 is +1, which I can write somewhere here. Okay, mod is absolute value is +1. Similarly, absolute value for -2 would be 2, absolute value for -3 would be 3, right? And here it would be 0, 1, 2, 3, 4. So these are actually the absolute value of t, which I have written just below this line. Now if I'm interested in right visualizing or representing this signal, I'm interested in the representing this signal x of t, signal x of t. I'm interested in representing the signal graphically. So for all positive values of t, this absolute value is positive, right? The absolute value is positive. A is also positive, we know this. It is already given that A is positive, right? So if A is positive, and for all positive values of t, for all positive values of t, the you have E, let me write it here. Let me write it here. For all positive value, I'll change this marker. For all positive value of, if t is positive, right, positive, e raised to the power minus a t, t is positive, right? So e raised to the power minus a t is basically yeah, or mod at, you can write it e raised to the power minus at. It's equal to e raised to the power minus at for all positive values of t. And this would be a decaying exponential, right? It would be a decaying exponential, for because for increasing value of t, the power increases. For increasing value of t, this power increases, and if this power increases, you can write it as 1 over e raised to the power minus a times t. It means the denominator increases, so actually this value decreases, overall value decreases, so the function value decreases. And for 1, if it has some value, for 2 it would be a smaller value, for 3 it would be further smaller, right? So you can always, you can see that the values are, this is actually a decaying exponential for positive values of t. For negative values of t, for negative values of t, as the absolute value are positive, right? If you take the negative value of t, if you take the negative value, for example -1, the absolute value is still +1, so you would have e raised to the power minus a mod of -1, which is basically equal to 1 over e raised to the power no, not 1 over e raised to the power, it would be actually it would be equal to, let me write it would be equal to e raised to the power minus a times 1, because absolute value of -1 is 1, so it would be minus a times 1, which is actually 1 over e raised to the power a. So this value, suppose it is this point. Similarly, if you have instead of 1, if you have t value equal to -2, so you can write it e raised to the power minus a times -2 mod, which is equal to e raised to the power, the absolute value of -2 is 2, so -2 times a, you can write it 1 over e raised to the power 2a, right? So this will be this way you can calculate each and every value, and you would see that the denominator increases within if t decreases from -1 to -2 and -3. So basically you would get a plot which is decreasing here as well, right? So a plot which is decreasing, the trend should be same, right? The trend should be, so it's just a plot something like this. So if you redraw this e raised to, let me redraw it on the new page. So if you redraw your signal, if you redraw your signal x of t, which is e raised to the power minus a mod t for a greater than 0. If you redraw it basically it would be it would look like this on the time axis. It would look like a decaying plot on the time axis, right? And at at t equal to 0, the value would be 1, because if you substitute, if you put the value 0 here, e raised to the power 0 is 1, so this particular value is 1. Similarly, if t is equal to 1, this particular value would be 1 over e raised to the power a, right? Similarly, at t is equal to 2, this would be 1 over e raised to the power 2a. Same value would occur at minus 1, 1 over e raised to the power a, and at minus 2, 1 over e raised to the power minus 2a. So if you join these, you would get this decaying plot, and you can do it for every instant of time because it is continuous curve. So basically this is your curve. Now if you want to write this, you can write this in another way, because we need to multiply it with a complex exponential, right? And then integrate it. So basically you can rewrite your signal x. Now if you observe this plot, from minus infinity up to 0, it's actually an exponentially increasing curve, right? An exponentially increasing curve. And you can say that, okay, we can rewrite our e a mod t. We can rewrite it as this one, which is basically we can rewrite it as e raised to the power a times t, which is an exponentially increasing. If you know that a is positive, so e raised to power at would be an increasing curve, and it would be similar to this one, from minus infinity to 0. This curve would be similar to this one. Now this part is not there, right? This part which I plotted as a dotted line, this would be the plot for e raised to the power at for an increasing exponential, right? So we can write, I can write it e raised to the power at, but I just need this portion. So I would say this is u of minus t. U of minus t is a unit step function, which means that this basically, this black curve here from here up to here can be represented as e raised to the power at u of minus t, plus this is basically, the other one is basically a decaying exponential, right? This is basically a decaying exponential, which I can say that this is just like e raised to the power minus at. Now I am removing that absolute sign, right? So this would be basically e raised to the power minus a times t u of t. So if we add this one with this one, we get this resultant signal x of t. Now there is no absolute sign here because I just replace this by these two signals, right? Because this would make our integral easy, x, because we have to complete x of j omega. So let me rewrite it now on a fresh page. Now after visualizing this signal, we can say that, okay, we can say that e of e a mod t can be expressed as e raised to the power a t u of minus t plus e raised to the power minus a t u of t, unit step function. So once we represent e of t in this form, it would make our integration easier. Now let me compute the Fourier transform x of j omega, which is the integral minus infinity to plus infinity and we have x of t e raised to the power minus j omega t dt. We have to compute this integration now. So let's do it step by step, and then we would see how we saw that we can write x of. Now let me replace this x of t in the uh, resultant. So we can write minus infinity to plus infinity, and x of t, I can write x of t as e raised to the power at e raised to the power at e raised to the power minus j omega t. Okay, let me write x of t only. Not, I'll just erase this one. Let me write e raised to the power at u of minus t plus e raised to the power minus at and u of t, and then we have the exponential. It is multiplied with this exponential dt, right? So we need to integrate this one now. If you observe closely these integrals, so exponential would multiply with this one, right? So let's do it. Minus infinity to plus infinity e raised to the power a times t and e raised to the power minus j omega t u of minus t dt. You have one integral, and then we would have a second integral. Which I can write as a summation. Let me write it below, right? Let me write it below. I'll write it the second integral, which is from minus infinity to plus infinity. We have e raised to the power minus at e raised to the power minus j omega t and u of t dt, right? Now let's try to integrate it. Now if you observe the first integral, we have the value of this product. The value of this product is only from because of this u of minus t. This u of minus t exists from minus infinity to 0 only, right, in this range. So the value of this product is only from 0 to from minus infinity to 0. So basically we have to integrate it from minus infinity to 0. The plus infinity integral, the limit of integration would change, right? So we have e raised to the power at. Let me write it jointly now. E raised to the power a. I'll take a minus j omega t, a minus j omega t dt. This is the first integral now. And the second integral, if you see, due to this function, which is exists only from 0 to plus infinity, the value of this product is from 0 to plus infinity. So the limit of integration would be not from minus infinity to plus infinity, it would change from 0 to plus infinity. And I can write this integral as minus, I'll take minus common, a plus j omega t dt, right? So this is how we can we have to integrate these two now, e raised to the power minus a plus j omega t dt. So we have two integrals basically. So let's try to solve it. Now it would become easier. Let me solve this integral, and it is this is e raised to the power a minus j omega t over a minus j omega, and we have to put the limit. Limit is from minus infinity to 0. Similarly, for the other one, we can say it is actually equal to 1 over minus a plus, no, not minus a, negative sign is outside, so let me write it actually minus 1 over, let me write it correctly. So this is basically, I will just replace that minus, I'll write minus sign here, minus a plus j omega e raised to the power minus a plus j omega t. So and the limit is from 0 to plus infinity. This is the limit. So let's try to solve it further. Here we have, let me write it here. Here we have 1 over a minus j omega multiplied with e raised to the power 0. E raised to the power 0 would be, let me put these limits, a minus j omega, and the upper limit is 0, so I have to multiply it with 0. Subtract the lower limit, which is a minus j omega. The lower limit is minus infinity, so if you put minus infinity here, multiply it with minus infinity, so it would be e raised to the power minus infinity. Now if I write the second term is, the upper limit is infinity, right? So 1 over a plus j omega, and you have the upper limit is e raised to the power minus infinity. If you put infinity is for this t, e raised to the power minus infinity minus e raised to the power 0, which is actually 1, right? 0 minus 1. Now if you rewrite this 1 over a minus j omega e raised to the power 0 is 1, right? This term e raised to the power 0 is 1, and this is e raised to the power minus infinity, which is 1 over e raised to the power plus infinity, and basically this term would be 0, right? Similarly you have this term is also 0 in upper limit. So if you simplify these integrals, and if you rewrite it, you can say that now here let me write it minus 1 over, complete this one, the upper step first. Let me complete this upper step. You have minus 1 here, so I have 1 over, from this one I have 1 minus j omega, minus and minus is plus, and plus j omega. So these two are basically your x of j omega. You can say your x of j omega is here. Now once you find this, because this is you can see that x of j omega is complex, and we can always rationalize it. We can always we try it in a standard form, so you can just rewrite it, because we are always interested in the amplitude and spectrum of this one. So if you can rewrite your x of j omega, you can rewrite it, or instead of doing it, okay, let me you can instead of writing it here, let me do it in a much simplified way. Let me now I have to write this x of j omega, but I'm just taking this first term, 1 over a minus j omega. If I divide and multiply it with a plus j omega, divide and multiply by this term, it remains the same, right? So you would get a plus j omega above. In the denominator, this is just like a minus b term. This is a plus b term. So a minus b and a plus b is a square minus b square. So I would write here a square minus b square, which is j omega square. Now you can rewrite this one as a plus j omega over a uh, a plus omega, a square plus omega square, because this j square is actually equal to minus 1. So j square omega square, you would get a square plus omega square in the denominator, right? So a plus j omega over a square plus omega square. Similarly, uh, let me do it. The Let me find. We have another term which is in this x of j omega, which is 1 over a plus j omega, right? 1 over a plus j omega. This term, this second term. So let's try to simplify this second term in a standard form. Now you can see that here why writing it in this form is feasible, because you can write, now you can see the real and imaginary part, right? You can see the real and imaginary part. If I want to write it, you can also write it as a over a square plus omega square, which is the real part, plus j omega over a square plus omega square, which is the imaginary part of this one. This is, which is the real and imaginary part. It's in a simplified form, like z is equal to a plus jb, in a simplified form. It's just like in this form now. So let me write the other one in the same form as well. So we have basically we have 1 over a plus j omega, which is the second term. It multiplied with a minus j omega, similarly a minus j omega, and if you simplify this one, you would get a minus j omega, and below this is a square plus omega square. And you can write this one, as a over a square plus omega square minus j omega over a square plus omega square. Now you can see the real and the imaginary parts in this one, right? So if we use these two, right, if we use this one, right, this is my if I use this one and the other one, this one, if I substitute these two, in the upper equation, in the equation above, in this equation, if I use in this particular equation, you can see clearly. Let me add these two terms. Now I would like to add these two terms. So if I add these two terms, it would be clear to you that adding these two terms would, see, this would be cancelled with this one. If you add these two, here it is with plus sign, here it is with minus sign. So your x of j omega basically can be written as the summation of this one and this one, which is just 2 times a over a square plus omega square. Now we just rewrite our transform, which is given by this expression x of j omega. Now once you compute your Fourier transform, you can draw it. Well, drawing it is you can draw it in the MATLAB, and if you draw this one in the MATLAB, you would see that basically this is your x of j omega would look like this function. If you draw it in the MATLAB, it would look like this function. Let your x of j omega, it's basically from this expression, right? So it would look like this expression, something like this. It would be something like this, right? instead of uh, rather it would be more something like this. It would be more like this. Now you can find some values on this plot immediately. For example, if you put omega, this omega equal to 0 in this expression, right? Put omega equal to 0, so you would have 2a square plus 0 square, which is 2 over a, right? It is 2 over a. So this peak value at omega 0 would be equal to 2 over a. Similarly, you can also find some other values at this omega axis. For example, if you put omega equal to a, right? Omega equal to a, so in the same expression, if you put omega equal to a, you would get 2a over a square plus instead of omega again you have a square. So basically it would be 1 over a. It would be 1 over a. So this particular value would be 1 over a. And similarly at minus a, you can find another value, and for minus, if you put minus a here in the same expression, it would be minus a square, which is a square. Again you would get 1 over a. So you can see that it's basically these are, you can find these values immediately. So on this particular plot, which is growing exponential and then a decaying one, like something like this, right? If you plot it on the MATLAB or Octave, you would find this plot. You can just plot this one, and you would see that a few points can be immediately identified. You can also find other points if you want. Just put other points, select other points, for example 2a, right? A, so you can also define the value for 2a. Similarly, in terms of a, you can have any other values, minus 2a. You can find these values immediately, right? So this is how you can plot the Fourier transform of x of t.